Hey everyone, welcome to The Explainer. Okay, today we are diving into a really brilliant new paper that solves one of the absolute biggest bottlenecks in artificial intelligence right now. We're looking at a breakthrough in how AI models handle memory, specifically this concept called cross-model KV cache transfer. Now I know that sounds super technical, but by the end of this, you're going to see exactly why it's a total game changer for the speed and the cost of the AI tools you use every single day.
So picture this. What if AI models could just instantly share their memories, like literally teleport their entire context to one another in a split second? Right now, passing knowledge between different AI models is pretty clunky. But imagine if one AI could seamlessly hand over everything you've just talked about to a completely different, much smarter AI without skipping a beat or pausing to reread the conversation. That is exactly what we're unpacking today.
All right, here's our roadmap. We are going to cover the AI context problem, what KV cache actually is, this super clever linear translation trick, how the mapper works, the massive need for speed, and finally, what this all means for smarter, faster AI agents.
Okay, Section 1, the AI context problem. Let's talk about the real-world headache of orchestrating modern AI systems. Here's the deal. Companies want to save money and computing power, right? So when you use a modern AI agent, they usually start your task on a smaller, cheaper model, say an 8 billion parameter one. But when things get complicated, the system hands the job off to a massive, much smarter 32 billion parameter model. The catch? Right now, that handoff is incredibly inefficient. The big model literally has to reread your entire accumulated conversation from scratch just to catch up.
So what's causing that massive delay? Well, that brings us to Section 2. What exactly is KV cache?
All right, quick refresher. The real heavy lifting in AI happens during the pre-fill phase. That's the initial, super computationally expensive phase where the AI reads your prompt and builds up its context before it types out a single word. Think of it exactly like a relay race, where instead of just grabbing the baton, the second runner actually has to run all the way back to the starting line just to do their leg of the race. It's just a huge waste of time and energy.
And the product of that exhausting pre-fill phase is the KV cache, which stands for keys and values. This is basically the AI's mathematical short-term memory. In our relay race analogy, the KV cache is the baton. And the researchers behind this paper realized something huge. If we can just figure out how to hand this baton directly from the small model to the big model, we save a massive amount of time and computing power. No more running back to the starting line.
But how do you actually pass that baton if the models effectively speak slightly different mathematical languages? Let's get into Section 3, a linear translation trick.
This part is absolutely fascinating. When researchers mapped the cache from a smaller QN3 model to a larger one, they saw these really bright, sharp, diagonal lines in the data. That was their eureka moment. Those lines proved that even though these massive neural networks are completely different sizes, they actually share a hidden, highly predictable, linear mathematical structure. In fact, a single layer from the smaller source model can actually explain up to 56% of the variance in the big target model's memory, which is kind of mind-blowing.
So, because of that hidden linear structure, we can totally change how these models tag team a prompt. Think about it. The old way, re-prefilling means reading the whole prompt from scratch. Terribly slow, incredibly expensive. But the new way? Cache transfer. Because they share that structure, we can just translate that existing memory directly into the larger model's format. We're trading an expensive, heavy reading task for a blazing fast mathematical translation task.
Now, let's look under the hood. Section 4, how the mapper works. We'll see exactly how this translation happens without breaking the AI's brain.
Here is how the new pipeline actually looks in practice. The prompt goes into the smaller source model, say a 14 billion parameter one. It generates its memory, its KV cache. But then, instead of the big 32 billion target model having to read the prompt, that memory goes through a linear mapper. It translates the memory, feeds it directly into the target model, and completely bypasses the target's prefill phase. The big model just starts answering instantly.
This linear mapper works in 3 super logical, clever steps. Step 1, it cherry-picks the top K source layers, basically just grabbing the most relevant layers of memory to translate. Step 2 is absolutely crucial. It strips out rope. That's the positional data telling the AI the exact order of the words. By stripping that out, the math translates pure meaning, so it works for a prompt of literally any length. And step 3, it just maps it all over using closed-form ridge regression. Clean, fast, linear math.
But wait,
What if the models are a bit too different, and that simple linear math doesn't quite perfectly align? Well, researchers found that for tougher pairings like the Ministrel family, they can swap out the linear math for a slightly more complex nonlinear network called an MLP. And the genius here? It can recover up to 37 percentage points of accuracy on reasoning tests. And it doesn't even do this by perfectly fixing the error. Instead, it cleverly sweeps those translation errors right into the AI's natural mathematical blind spots, literally hiding the errors in the parts of the memory the AI naturally ignores anyway. Just brilliant.
All right, Section 5, the need for speed. Because at the end of the day, all of this architecture is in service of one thing, and that's going incredibly fast.
If you only remember one thing from this explainer, make it this single number, 25. By mapping the memory this way, the target AI can get to work up to 25 times faster than traditional reprefilling. 25 times! It is an absolute paradigm shift for efficiency.
To put that speed into perspective, imagine a massive 32,000 token document, a really, really long chat history. If the big model has to reread that from scratch, you're sitting there waiting almost 7 full seconds. But with this KV cache transfer, that wait time plummets to just 277 milliseconds. You literally don't even have time to blink before the smarter model has taken over and started typing. The user wait time is completely gone.
Let's bring it all home with Section 6, Smarter, Faster AI Agents. Let's talk about what this means for the software we use every day.
Now, you might be thinking, okay, but doesn't translating memory that fast cause the AI to hallucinate or get confused? Actually, the data is super reassuring here. For top model pairs, this linear mapper retains up to 98% of the AI's original standalone accuracy. And even better, across really long 10-turn multi-part conversations, the handoff stays completely stable. The AI doesn't drift off topic, it doesn't forget the context of your chat, even though its memory was basically artificially teleported right into its brain.
To sum up the real-world impact, I want to point out this observation right from the researchers' conclusion. They state that skipping this reprefill reduces serving cost, energy, and latency for agentic workloads. So this isn't just some cool math trick, right? It's the key to running complex, multi-agent AI systems that are vastly cheaper for companies to host, way faster for you to use, and dramatically more energy efficient for the planet.
So I'll leave you with this final thought. We are stepping into an era where AI models act a lot more like a seamless team of specialists rather than single isolated brains. When these distinct models can just instantly teleport their context and lived experience to one another in milliseconds, passing the baton without ever dropping it, what entirely new limits are these multi-agent systems going to break? It's a wildly fascinating future, and it definitely just got a whole lot closer. Thanks so much for joining me on this explainer.